Could a black hole make a binary star fizzle out? Why do we get a flash of neutrinos before we see a supernova explosion? And could there be antimatter galaxies out there in the universe? All this and more in this week's Question Show. It's time for the Question Show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops into your brain, just write it down and I will gather them up and I will answer them here. Like, it doesn't matter if it's about the video that you're watching, just if a question pops into your brain, write it down. And to be honest, there haven't been a lot of questions coming in. So I need more questions. They are the fuel that runs this channel. So please, if a question pops in your brain, I'm your guy, give it to me. All right, now we record this show every Monday at 5 p.m. Pacific time. So if you want to participate in the show live and have your questions answered, see follow-up questions, chat with the delightful community, please come join this. All right, let's get on to the first question. Delta Infinium 869. Can a red giant star currently burning helium with a black hole or other compact binary partner fizzle out due to the compact object tidally stripping away so much of its envelope and mass that the core pressure is no longer high enough to permit helium fusion? What would such an object look like? All right, I'm going to go into a bunch of binary star types that sort of meet what you're talking about, because this happens quite a lot in the universe. So there's like 4 main kinds of interacting binaries. Like, there's plenty of binary stars where the stars are far apart, but we're looking at the ones that are interacting. So we'll sort of consider the partners in the situation. So in one situation, you've got a main sequence star, and then you've got, say, a white dwarf star or some other kind of compact object. And because of the tidal forces from a black hole, from a neutron star, from a white dwarf, they are going to be able to strip material off of this main sequence star and feed on it. In the case of a white dwarf star, it's going to eventually accumulate enough material that's going to detonate as a supernova. If it's a neutron star, we kind of don't know what happens, but like, it'll probably turn into a black hole at some point if it gathers enough material. And then the last possibility is a black hole, and a black hole just becomes more black hole. And actually, astronomers can see the differences depending on which of those situations it is, based on the kinds of radiation that is coming from the system. So if it's a black hole, they call this an X-ray binary because there are these regular flashes of X-rays every time material is falling into the black hole and getting consumed. While, say, with a white dwarf star, they can call these cataclysmic variables. So you're seeing these flashes that are coming, but it's not like black hole level. And that's the object that's doing the feeding. But I think your question was like, what's happening to the object that is being fed upon? And so when you have binary stars that are really close together, and they have to be really close, what you'll get is a donor star and then an accreting star. So the donor star is the one that is supplying the material, and the accreting star is where that material is being accreted. And again, you need special situations. The stars have to be very close. And what you can have is like one situation where you had a star that was in a main sequence phase, and then, as you say, it goes into its helium burning phase and it expands out and its envelope increases. And around stars, you have this sort of balance of gravity, where if it's just the star by itself, then it can hold on to all this material. But if it has some kind of binary partner, then you get this region, and astronomers call this the Roche lobe. And this is where, essentially, if the material goes beyond this level and it's close to the binary partner, it crosses the gap and joins the accreting star. And if it's sort of ferocious enough, you can absolutely turn back the clock on a giant star. You can strip enough of its outer envelope away that the star will start to decrease in mass, decrease in size, and sort of downgrade through the class of star that it is. And so maybe it was set to become a giant, like a super giant star, and it was going to detonate as a supernova, but it's feeding all this material to its partner, and then that partner will become more massive, and the donator star will become less massive and sort of be pulled off of supernova alert. Now, the donor star now has been gaining a pile of material, and so it is probably inevitably going to become a supernova now that it's gathered all that additional mass. You're sort of switching from the one star that was going to cause a supernova, or at least had gone into a red giant star phase, and you're feeding it all to this partner star, and then it's going to suffer the consequences of all this additional material. But these things are out there and they can see them, and it's pretty amazing. I'm sure you've noticed the Star Trek planet name that has appeared above my shoulder, and this is a way for you to vote for the question that you thought was the best. And so last week we had the most votes for Andoria, which is that people were wondering how rogue planets could have liquid water on the surface even if they don't have a star. So I'm glad the majority of you liked that question and the answer. So once again, watch through this entire episode. A different planet name will appear as I give a different answer, and then at the end, put the name of the planet in the comments down below, and then we'll add them all up and we will celebrate them here next week. Sandy VB. How do we get a flash of neutrinos from Betelgeuse's explosion before the actual light of the explosion reaches us? Does that mean that the neutrinos travel faster than light? So whenever I mention this amazing fact that neutrinos arrive before the light from a supernova, someone will always ask this question. And I'm sure I've answered it many times in the past, but I love it so much that I'm going to explain it one more time. So when you get a supernova, you've got a giant star that is under so much gravitational pressure that it's wanting to pull itself inward, but you've got the fusion at the core of the star that's pushing outward. And so the star is in this balance, this equilibrium. And then inside the core of the star is sort of shifting up through higher and higher elements, and eventually it reaches iron. And iron produces no energy when it fuses. And so there's no longer the outward force, the radiative pressure, there's only the inward force coming from the gravity, and so the star just collapses inward, piling up. And what you get is down at the very middle, as the star is coming in, it's going faster and faster. It can go like 70% the speed of light. Like, it is coming together really quickly. And it's that force that generates the neutron star or the black hole at the middle. And then you get this sort of bounce of material. All this energy and material piles up, and then it detonates as a supernova. But while this is happening, while all this infalling material is coming inwards and all this energy is starting to build up inside the supernova, the energy can't get out. It's blocked by all of this matter. And so it has to sort of random walk around inside this stellar material. But at the same time, these neutrinos are being formed, and neutrinos can pass through like a light year of lead and not interact. And so the neutrinos escape immediately. And the neutrinos move at 99.99, like some significant fraction of the speed of light, and they get out immediately. And then it takes a few minutes for the light to be able to get out of this explosion that's happened. And then the light is able to reach space, and then it makes the journey towards our eyeballs. But the neutrinos have enough of a head start that we'll get notice. We'll get like a couple of hours notice before the radiation shows up. And what's really amazing about this then is that you could set up really powerful, very sensitive neutrino detectors and listen for bright flashes of neutrinos. And if you get that flash, then you know where a supernova is about to happen. And then you turn your telescopes, watch the star as it dies and then explodes as a supernova. Now, right now, the best neutrino detectors in the world can only really do this for a few hundred light years. There's a new Chinese neutrino detector that's going to be coming online that maybe will do this out to like a couple of thousand light years. And so we would need a Betelgeuse, right? We would need a supernova to go off very close. But if one did, we would get the advance notice. And I really like this idea. Neil Greening 9609. In the big universe, trillions of times farther than we can ever see, could there be vast swaths of annihilated nothingness and then antimatter galaxies? So the question you really ask, like one of the big mysteries in astronomy is, why is there more matter than antimatter? It was believed that there should have been equal amounts of matter and antimatter at the beginning of the universe, and then they would have met each other, they would have annihilated, and then you would have been left with just energy. But for some reason, there was a little bit more matter than antimatter. You got that annihilation, but you're left with more matter and no antimatter. And this is like, I don't have an answer. Like, this is an unsolved problem in astronomy. But could that just be a local issue? Could it just be that we have more matter here, but there's other places in the universe where there's more antimatter? Maybe. Like, it would have to be over the cosmological horizon, because when matter and antimatter are annihilating, the results are gamma radiation. And so astronomers have looked in the sky in all directions, built large surveys. They're looking for gamma radiation, and they don't see it. And so we don't see the results of matter and antimatter meeting at the vast scales across the universe. So if this is happening, then it is, then our observable universe is weirdly matter dominated, but other parts of the observable universe would be weirdly antimatter dominated. And you're right, that there would be these regions where the matter and the antimatter would have annihilated each other, and you would have just nothingness. And then eventually the balance would shift in one way or the other, but we don't see it. And there was new research that came out like last week, which sort of really helped sort of sort this out in one way. And that is that it appears that antimatter falls down in gravity in the same way that matter falls, is attracted by gravity. I know it's like, that's not the right way to exactly describe it. But the point is that if you drop a chunk of antimatter on Earth, it's going to fall down, hit the surface of the Earth, explode. It's not going to fall up. And this is one of the questions. Like scientists were pretty sure, and Einstein's theories predicted that antimatter should fall. But one possibility is that antimatter would fall upward, that it was actually anti-gravity. And this was exciting because if that's the case, then you could build warp drives. Like one of the keys to building a warp drive is you need some way to have like negative gravity. And maybe if antimatter produces anti-gravity, then you're partway there. And so researchers at CERN were able to do an experiment where they were able to generate particles of antimatter, anti-hydrogen, and they were able to drop it in a gravity field. They built this sort of chimney where they were dropping the antimatter, and they were able to determine that this was falling down due to gravity. And like, it's a really tricky problem. Like, you imagine, as soon as a particle of antimatter touches any part of the outside, then it's going to detonate and you're not going to get a great result. So they had to be able to confine this antimatter while they were dropping it. And so when you sort of take that result and then you sort of expand it back out to the universe, and you think about like, okay, if matter and antimatter repulsed each other, then you would expect that the matter would sort of pull together into its galaxies and the antimatter would pull into its anti-galaxies. And if they got too close, they would sort of push each other away. And so you could have these separate universes, but now it looks like they attract each other. And so wherever you're going to have matter and antimatter, they're going to find themselves together with gravity, and then they're going to annihilate, and then you're going to get all this radiation, and we would see it. And so if it's that, then it's way over the cosmological horizon and we can't see it. Josh Levis 8076. Are there any theories that explain the implications of Earth being the only planet to produce life? Yeah, of course. Someone had to be first. And so maybe we do live in a universe with countless intelligent civilizations, but someone had to be first. And whenever that civilization showed up in the universe and they looked around the universe and everything looked like a pristine wilderness, they said to themselves, that's weird. I mean, where is everybody? There should be millions and billions of alien civilizations out there, but they were first. And are we first? I mean, when we look out in the universe and we see what appears to be a pristine wilderness, we see stars not enclosed by Dyson spheres. We see stars that are in random collections of galaxies, not nicely organized. We see planetary systems that aren't in the perfect configuration for the maximum amount of resources. We see stars that could be torn apart and turned into red dwarfs that would then provide the right amount of energy for the longest period of time. We don't see any of that. We see what looks like just, a raw forest, but in galaxy form. And so maybe we're first. Someone had to be first. Could be us. Biggles Tantan. If you could travel anywhere and any time in space, when and where would you go? I mean, the problem, like the fundamental problem with this question is that we know so little about the universe. Like, we really just know about this one planet, and we've got some images of the moon, some images of Mars. We've seen some bad images of the surface of other places, and like, that's it. And so we don't know what is the most interesting places. Like, I wish I could take all of the interesting features of the entire universe and then sort them in this big list for like deepest chasm, craziest volcano, weirdest ecosystem, and then I would go there. Now, obviously, there are places and things that we know would be pretty fascinating to look at. Like, I would like to see what it would be like to be on a star near the center of the Milky Way, where you have stars that are like 1,000 times more dense than what we have out here in the outskirts of the Milky Way, where just the entire sky was filled with bright stars. That'd be weird. Or to be inside, say, a globular cluster where stars are like 1 light year away from us as opposed to 5 light years away from us. That would be pretty amazing. Obviously, I would like to be able to see very dramatic events up close. I'd love to see the event horizon of a black hole, the accretion disk swirling around safely would be nice. You know, a lot of the things that I think people would love to see, they think they would love to see, actually wouldn't look that good. Like, wouldn't it be cool to be able to be near the pillars of creation? But the problem is that they wouldn't look very good without a long exposure camera system. Or wouldn't it be cool to see when Andromeda and the Milky Way are merging together, but actually it wouldn't look very good without a long exposure camera? Or like, what would it look like at the beginning of the universe when galaxies are going through their starburst phase, when there was 100 times more star formation than what we have today? So I don't know. Like, I think step one is figure out everything that's out there, and then I'll get back to you when I've got a nice comprehensive list of all the cool things to see. Bravo 01. Was the mechanism used on OSIRIS-REx asteroid sample similar to a home vacuum cleaner, just in reverse? Kind of. So what they did was they had the sample container at the end of this arm, and then OSIRIS-REx got really close to the surface of Bennu, and then they put it onto the surface of Bennu, and then it puffed out a bunch of gas that sort of pulled the stuff off of the surface of Bennu, and then a bunch of it went into its collection capsule, and then it kicked itself off of the surface of Bennu. So yeah, I mean, if your vacuum cleaner would only just run for just a second or two, and then that was that, but in reverse, yeah, that's about right. I mean, think about how tricky it is to blow compressed gas in a vacuum while you're approaching a asteroid that is rotating and filled with boulders. Like, it was a pretty challenging grab, but they got it. And I mean, now we know they got about 250 grams of material from Bennu, and so that's like going to be plenty to be able to share with lots of people. Two Rivers Observatory. When was the last time you got to have some eyepiece time for yourself? Like eyepiece time, like looking through a telescope eyepiece, or eyepiece time, like doing astrophotography with a telescope. I mean, every couple of nights we get the binoculars out because there's interesting things to see in the sky. The moon, Saturn, Jupiter, comets have been around. Lots of pretty great stuff in the summertime, looking at the Milky Way and stuff. So I'd say we have the binoculars like right beside the couch. And so we're using it during the day to look at birds, and we're using it at night to look at the sky. Looking through a telescope eyepiece, it's probably been a couple of months. I've got a telescope behind me there that I had set up and I haven't used in a couple of months. I need a new telescope. I'm probably going to get a Dobsonian. Just, you know, I talk about it all the time, and the telescope that I have is sort of too complicated. I don't want to use a Dobsonian. And then, of course, it was a couple of years ago since we were doing astrophotography on the virtual star parties, and I really want to get back to that. Like I think that's one of the most fun things that we've ever done, where we're live streaming the view from telescopes, and we're taking pictures, and we're explaining the night sky with lots of people and special guests, and it's like fun, but also astronomy and kind of chill, and I really like it. And you know, that is like, at some point I'm gonna build a proper little observatory here and set it up, and then continue on with the virtual star parties. I know I keep saying that, and so like you keep reminding me, and so at some point I will proceed. So you might not know, but I talk to the patrons. When you sign up as a patron of my channel, I send you an email and ask if you want to have a chat with me, and it's literally me. We're having a conversation, and I have a bunch of questions for you, and I hope you have some additional questions for me, and that's sort of one of the benefits of becoming a patron. So if you do become a patron and you get that email, it's really me. You really will get a chance to chat with me. So definitely, if having a chat with me is one of the things that you want and you consider valuable, consider joining our Patreon. Go to patreon.com/universe today. And I'd like to thank all of our subscribers, including our recent newcomers, Ryan Orman, Big Dips, Dustin Cable, Antonio Lofilara, Stanley Harrison, Paul Gowland, M, Mitchell Altschuler, David Duer, and Fred Schroeder. Join the club at patreon.com/universe today. Lance Piles. Europa, Enceladus, or Ganymede, which do you give the highest chances of finding life? Finding life, it's going to be Enceladus. Like with Enceladus, we've got these tiger stripes at the bottom of the world. It's blasting water into space. You can fly a spacecraft right through that material and sample it and detect if there's amino acids. There's actually a paper that I looked at like just today where people were proposing sending light sails to Europa and Enceladus. And so you could fire a 100 kilogram spacecraft to Europa or Enceladus. It would take you about 1 year to get to Europa, take you about 4 years to get to Enceladus, and it could go through the plumes and detect the presence of amino acids in the plumes, and you would just get an answer. And so I think, practically speaking, the best place to look is Enceladus, just because it's the easiest place to search. It's the low-hanging fruit. The place that I think is most interesting is probably Ganymede. You know, Ganymede is large, has a ton of water on it. It's got a fairly large core. It's going to probably have more radioactive material in it, more heat that's being produced, just a larger place. And it also has an internal magnetosphere. It has some protection from radiation from space. So I think that's my favorite world. You know, I keep saying this, Ganymede is the new Europa because it is just such an exciting place for us to explore. I'm really glad that the European Space Agency is sending their JWST mission and primarily going to Ganymede. Everyone's focused on Enceladus and Europa, but Ganymede is the place. That's going to be the goods. Brother Sly, will JWST and Hubble see the same gravitational lens? Absolutely. You know, when it comes to gravitational lenses, the Hubble Space Telescope is sort of the finder scope for JWST. Like a lot of the gravitational lenses that have been found with Hubble, and in fact, like gravitational lenses are so useful that now astronomers are looking through gigantic data sets of information. Things like the Sloan Digital Sky Survey, where they're looking at millions and millions of galaxies, or the Dark Energy Survey camera, again, looking through millions of galaxies. And then it's a machine learning problem. They know what a gravitational lens looks like. They feed all of these plates into the machine learning algorithm, and it sort of looks at each galaxy and goes, oh, here's a weird one. What's going on here? And then an astronomer can go and take a look at it and go, oh, that's a new gravitational lens. There was a new Einstein cross that was found fairly recently by a machine learning algorithm. And they found it's beautiful, like a perfect Einstein cross where you've got like the central galaxy and then you've got the lens galaxy above and to the sides in this sort of perfect, you know, cross formation. And it was found using a machine learning algorithm. And so we're at the point now where we have these giant surveys of the sky. You find all the gravitational lenses in them, and then you observe them with whatever tool works best. Sometimes it's Hubble if you want to make observations in the visible spectrum, and other times it's going to be with JWST if you want to look in the infrared. And like when you're looking at a gravitationally lensed galaxy with Hubble, you are, say, seeing a galaxy as it looked maybe 1 billion years after the Big Bang. And like, that's really interesting. You know, it's very early on, but if you're looking at a gravitational lens, the right kind of gravitational lens with JWST, now you're looking at galaxies that are 400 million years, 300 million years, 200 million years after the Big Bang. Like these are the places where the first stars that were ever forming. And so, you know, one of the big mysteries is, what did the first stars look like after the formation of the universe? And it's, you know, Webb can't look at them directly, but it can look at them through a gravitational lens. And so the hope is that at some point things will line up and a gravitational lens will be found, probably, you know, through some other way, like maybe through the Nancy Grace Roman telescope, because it's also infrared. And then that lens will be observed by Webb, and maybe we'll get some glimpse at the earliest moments of the universe, just a few 100 million years after everything formed. So the gravitational lenses are features of the sky that if you knew where to look, you could look at the gravitational lens. It's not like they're shifting and changing very quickly. Unlike gravitational microlensing, like when we find planets, that lens only lasts for, you know, an hour and then it's gone forever. But with the big lenses, yeah, they last effectively forever from our perspective, for the human lifetime. Shane McKinley, could we be in a black hole universe? So this is a theory that has been floated that our entire universe is actually inside a black hole. And there's like an interesting coincidence, which is that if you take all of the mass of the observable universe and you imagine like all of the regular matter, all of the dark matter, and you sort of mash it into a singularity. And then you said, well, like how big of a black hole would that be? What would the event horizon of a black hole with all the mass in the universe be? And all the energy, right? It would be the size of the observable universe. Like the event horizon of a black hole that contains all the mass in the universe is the size of the observable universe. That's weird. That's a coincidence. And it is probably just a coincidence that give us a few more billion years and those numbers won't match anymore. Sort of in the same way that the moon and the sun are the same size visually in the sky today. But that wasn't always the case. It's just a coincidence. Like something had to be the same. But, that interesting coincidence has caused people to wonder like, oh, are we living in a black hole? And then are the black holes that are in our universe, like, do they contain other universes? And are there people inside those black holes wondering if they're inside a black hole and then there's black holes all the way down? Maybe, but there's no evidence that that's the case. And so nobody has taken it that seriously, but there are science papers that propose that our universe is inside a black hole. J. Cross, what do you expect to be reported about the OSIRIS-REx sample next week? Oh man. I wasn't expecting for us to hear the amount until next week. And so I'm kind of surprised that we got the announcement of the 250-ish grams of material. Like I figured they were going to save that. But I think it's too early to do any science on the OSIRIS-REx samples, to do good science. Like you could obviously like grab a little bit and weigh it and measure it and run it through a mass spectrometer and, light it on fire and try to figure out some interesting provisional information, but it's going to take a while. But when you sort of think back to what happened with the Hayabusa 2 mission and the scientists who got their hands on the samples, they actually did come out with some results pretty quickly. And then we've been getting more and more updates from them as they're finding more amino acids in the samples and getting a much better sense of the amount of water that was present at the beginning of the solar system. So I think I would expect this early from when they gathered the samples for them to, more logistics type stuff. Like we got the samples, they're in place. Here's all the people who are going to get access to it. Here are some of the big questions that we have now that we have the samples in place. Here's how we plan to deal with them, that kind of thing, as opposed to actual results. We figured out where water came from. We found another 17 amino acids that nobody's ever seen before. We've determined that the early solar system was made out of these chemicals and those chemicals. That's the kind of stuff that we will find out, but I don't think we'll get it super early on. Shane Cooney, what's the solid mass at the center of Jupiter? When you go inside Jupiter, like, what is gas? What is hydrogen? These things don't make sense in the same way anymore because you've got enormous amounts of pressure and temperature. Like if you went down into the center of Jupiter, hydrogen itself would just become thicker and more dense. And eventually you'd be like moving through hydrogen, which is a gas when you let it out into, say, Earth's atmosphere. But when it's under that kind of pressure, it's like a fluid. You would be swimming through hydrogen. And then after a while, it's so dense that it becomes like a metal. And at the center of Jupiter, the temperature and pressure are ludicrous, like 25,000 Celsius inside Jupiter. Very hot and very high pressure. And so like you would need a pickaxe to get into the hydrogen in the middle of Jupiter. And you would dull your pickaxe as you would need a diamond bit to get into the hydrogen. But of course, inside Jupiter, there's also other heavier elements. So there are several Earths worth of rocky material and metals, like regular metals, not hydrogen turned into metal, but regular metals, iron, nickel, gold, all of that kind of stuff. Everything that we've got on Earth is inside Jupiter, but several times over. And so when you think of a gas giant, like, oh, Jupiter's a gas giant, we could just like fly my spacecraft into Jupiter and then I could land at the solid core. No, it wouldn't be anything like that. You'd be like, I try to fly into Jupiter and then I get crushed by the dense sort of liquid of Jupiter in its upper areas, and then I get crushed as my spacecraft falls down and down into the planet, and eventually it just gets added to the rocky core at the center of it. Wagism. Is it feasible that gravitational waves could be a possible energy source for mankind? Theoretically, yes. So when a gravitational wave is passing the Earth, you are extracting energy out of the gravitational wave. You can't make the detection of a gravitational wave without extracting a tiny little bit of energy from the gravitational wave. And so you could put it to work. You could like light a little LED light. But it's much less than that. And so it's really about the efficiency of it. But theoretically, you could extract power out of the gravitational wave as it moves past. Andrew Cornelio. I read that JWST found rogue planets. How do we detect rogue planets? Don't we detect planets by periodic dips in their host star brightness? Yeah, this is really exciting news. This is a big story that just came out this week. And so there was like a giant mosaic of Orion Nebula produced by JWST. And like this picture is going to be in the running for picture of the year for JWST. It's a stunning image. And I hope at this point, Chad has shown this gorgeous image. But there was a lot of science papers that went along with this image. And one of them is that astronomers have found hundreds of objects in the nebula, which are roughly the mass of Jupiter and lower. So 0.6 mass, Jupiter mass. So a little more massive than Saturn. And they found hundreds of these things in the Orion Nebula. So how did they find them? And so with JWST, it's very sensitive to objects that are glowing in infrared light. And so it has such resolution and it's so sensitive that it was able to spot these objects, essentially newly forming rogue planets. Now, if I remember, 9% of these objects were in binary systems with other stars and such. And so, they're all newly forming, just like the rest of the stars in the Orion Nebula. And when you've got objects that are newly forming, they're releasing heat, and JWST was able to detect them. Once these objects have gotten cooled down and they're no longer easily visible in the infrared spectrum, then you do need some other way to be able to detect these rogue planets. And the main way that astronomers are going to be doing this, or have already done this, is with gravitational microlensing. So you are staring at a vast field of stars, and then you're watching as the light from one of these stars gets distorted as an object passes in front, essentially becomes like a lens to the star itself, and it sort of wobbles in a way. It takes minutes to a few hours to sort of change in brightness as this object passes in front, and you can determine the mass of the object purely by how the light is distorted. And astronomers have found these rogue planets this way. I mean, they found they've found stars with planets, and they've found just completely standalone rogue planets. And the machine that's going to find many more of these is probably going to be the Nancy Grace Roman telescope. It's going to be looking at very large fields of the sky. It's going to be looking for changes in brightness. And so it should be able to map out probably thousands of rogue planets in the field of view. And so, no, you don't need a star. You don't need to be watching a star to see the planet passing in front on a regular basis the way you would with an exoplanet. It's more like you're watching all the stars and you're watching for any of them to change one time, and that tells you that the rogue planet is there. Now, there are almost certainly going to be rogue planets in our neighborhood. I mean, if they saw hundreds and hundreds of them in Orion Nebula, these things are common. And so you can imagine future infrared observatories that are very, very sensitive and very powerful could start turning up rogue planets just in our area within a few light years of Earth. The closest example of a telescope that did a very similar search was called WISE, and it was an infrared telescope that was looking for large objects in the outer solar system. It was looking for Planet 9, or like, does the sun have a red dwarf companion or a brown dwarf companion that comes by on a regular basis? And WISE was able to rule out entire classes of objects because it was so sensitive. It should have been able to see it. It didn't see them. So it was able to rule out like there are no objects with the mass of Jupiter within 50,000 light years of Earth. But smaller objects could be out there. And so Planet 9, whatever it has to be smaller or has to be larger and farther. And so hopefully, now that we know that these rogue planets exist, and now that we that there could be a lot of them, I think there's going to be a real increased demand to try and observe them and find them and map them out. And I always sort of have this romantical notion, right, that we thought that our closest star was Proxima Centauri, but in fact, there could be a dozen rogue planets between us and Proxima Centauri, and they could be the stepping stones that you could move out into the Milky Way, not by going from star to star, but by going from rogue planet to rogue planet. And then it sort of breaks up the journey into much smaller pieces that are maybe a lot more feasible. So, rogue planets are one of these sort of surprising discoveries, but one of the most exciting fields for the future. I mean, if you were planning to be an astronomer, or you're just finishing up school, you're like, what do I want to go into? Rogue planets. The bittersweet. Have we discovered any exomoons yet? What are the most verifiable discovery methods that we could use to find one? At this point in 2023, I don't know of any confirmed exomoons that have been discovered. I'm weirdly friends with the exomoon community, and so every time I talk to them and do an interview with them, I'm like, have you found any exomoons yet? And they're like, oh, we've got one that we think we like, and we're going to publish a paper soon, but it doesn't come out, and so we're still waiting. So to see an exomoon, it's a really challenging observation. You've got to not only see a planet that is transiting in front of a star, but then you've got to have the moon also contributing to the amount of light that's being blocked on the star. And so sometimes you're going to get where you're seeing it like star and then the planet, and then the moon is right in front of the planet. And so other times the moon is just to one side of the planet or the other side, and so it's contributing to the dimming of the star. It's a very, very challenging observation to make. And so it requires an enormous amount of data. You've got to watch the star. You can't just watch the star 3 times and go, found a planet, the way you can with exoplanets. You've got to see so many transits of the planet going in front of the star so that you can tease out that additional signal of the exomoon. I mean, the reason to find exomoons is gigantic, because exomoons turn uninhabitable gas giants into habitable worlds. You've got Endor, right? You've got the forest moon of Endor. It's gas giants orbiting around a star. Gas giant is in the habitable zone, but the gas giant sucks. But then you've got these moons around it that are worlds in themselves, that could be Earth-sized, and they could be in the habitable zone, and they could have liquid water on the surface, and they could have life. And suddenly planets that were uninhabitable now become habitable. And so there's a real reason to find it. And so the race is on. And I think the way an exomoon will be found is that someone will stare at a transiting exoplanet long enough to pull a signal out of the noise. And that's going to take a ton of observation time on the best possible candidate. And that's just going to take a while. John Dopeker, curious of your thoughts on the claims that nuclear propulsion could get us to Mars in less than a month. Seems far-fetched to me. Is it really possible? A month seems far-fetched to me too, but 3 months, 90 days, that's perfectly reasonable to get to Mars. Now, getting to Mars very quickly is one part of the problem. Slowing down when you get to Mars is the other part of the problem. And so the answer to that is to aerobrake. So you fire your nuclear rocket, you get an enormous amount of velocity, you get to Mars, you go through the atmosphere and slow yourself down multiple times if it takes to go into orbit around Mars. So a nuclear rocket would be a total game changer for flights within the solar system. I highly recommend it. But missions to Mars right now take around 9 months to about a year. And that's because they follow this very specific trajectory called a Hohmann transfer. And it's designed to use the absolute minimum amount of fuel to make that journey. And so, yeah, theoretically, a nuclear rocket could make the journey from Earth to Mars in a shorter period of time. I've heard 90 days, 3 months, but maybe you could go shorter than that, depending on how you configure your rocket and your payload and stuff. But I still think that probably a nuclear rocket is going to follow a Hohmann transfer. They're going to take that 9 months to make the journey, because that's the one that allows you to use the least amount of fuel. And if you have the least amount of fuel, then you get to have more room for payload. And that's going to be really important. So I think, we know that human beings can live in space for months at a time. We can live for a year in space or longer. And so now it's just a question of, can we survive farther away from Earth for longer periods of time? And I think the answer is yes, right? Like, I think we can figure out this technology to be able to get there. And I think it's better to have more cargo, more payload, more supplies for astronauts than trying to pare everything down and just make that journey in the shortest possible time. Although you get to minimize the amount of radiation damage that the astronauts take. So there are definitely some advantages to going quickly. But I think first we go safely, then we go safely and quickly. All right, so those were all the questions that we had this week. Thank you everyone who participated. Now I'm going to talk a bit about some media that I'm really looking forward to, but first I want to thank some of our patrons. Thanks to Mark Anstis, Joel Yancey, Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Schipelin, Jay Dennis, David Giltonad, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbeoff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level, and all of our other supporters on Patreon. So a TV show that I'm really excited about is coming back shortly on Apple TV, and that is For All Mankind. And so they're into season 4 now. And if you haven't watched this show at all, I urge you to watch it. Like, it's worth signing up for Apple TV for 1 month and then watch For All Mankind, and like maybe watch Ted Lasso and Foundation. Like, there's a bunch of shows that you should watch. I'm not being sponsored by Apple TV. They couldn't afford me. But For All Mankind, it tells this sort of alternative history of like what would happen if the Soviets were the first to land on the moon, and then this set off this new space race. And so instead of the Soviets N1 rocket failing and then them just not being able to make it to the moon, and then the Americans landed and then they sort of fizzled out, what if it was just an ongoing race? And then all of these really cool space technologies would just grow and grow and grow. You would have more missions to the moon, and then you'd have missions to, you have a space station built much earlier on, like maybe in the 80s, and then you would have astronauts going to Mars in the 90s and so on. And we have more and more exploration of the solar system. Like, all of these things were possible at the time. It's just there wasn't the budget and the political will. But this show asks, what if there was? And, whenever I watch it, I'm extremely impressed by the quality of the technologies that they talk about. Like, you see a Sea Dragon launch, which is amazing, as well as space shuttle powered with a nuclear rocket and things like that, and the kind of infrastructure that we might expect to see if people were serious about exploring space. And the characters are good, and I think it's a great show. And so season 4 is coming back November 2023. And so if you want to kind of catch up, if you haven't seen the show, you can catch up, watch all 3 seasons just in time, about a month from now, to be able to then watch season 4 with the rest of us. So yeah, For All Mankind gets my vote as one of the best space-related TV shows really ever made. All right, let me know what you think, and we'll see you next week.